myself to the stream. I should add myself to the stream. Hey, what's up, everybody? Good morning. How are you? Good evening. Good afternoon. Welcome to the weekly VS Code live stream. It's Thursday, here at least, 10 a.m. in Nashville, Tennessee. And today, we've got a good stream for you. We've got Seth Juarez, who needs no introduction. What's up, Seth?
Hi.
You do need an introduction, though, because nobody knows who you are.
I'm like, I'm famous in like very specific places with five people, maybe. And
Right. So
three of them are related to me.
For the few people who don't know you, who are you and what the heck are you doing here?
My name is Seth Juarez, and I work in the Azure AI Platform Group as a program manager. My job is to help tell the story of AI with respect to how to do it in the cloud.
That sounds super exciting. Thank you for
delightful.
That. Yes. And what are your qualifications other than that super fancy title in a group that it sounds like you make robots?
No robots yet. My qualifications is I don't know. I dabble in machine learning. I went to school for it. I was a .NET dev for nigh a decade, and then I was like, I'm going to go back to school and better myself.
Wait, so I went and learned about. You were a .NET dev, and then you said, I'm going to go back to school and better myself. Okay.
Yeah, but not that I was going to be better than a .NET dev, because .NET devs are fantastic.
Well, my first memory of you is we met at a conference, and you were doing a session on machine learning with C#, and this was like 2011.
Yes.
And you were working somewhere else. And I thought, no one's going to go to that session because that's not even a thing. And then so many years later, I'm kind of wrong about that.
Well, there was like 8 people there. And when I think it was at Codestock. Wasn't it Codestock, I think?
I think so, in Chattanooga, Tennessee.
We stayed at the Chattanooga Choo Choo.
That is correct. That's an actual place, chat. Yeah.
Fantastic location. And there was literally like 7 people there. And I was like, y'all don't understand. This is some goodness. So
this is going to be a thing. Well, what are we doing since my qualifications here to host a streamer that I don't know anything about machine learning. And so what are we doing today? It's like a gentle, what was the title? I've forgotten it every time. A gentle introduction.
A quick guide to machine learning. I'm going to talk about machine learning in a way that a programmer gets. And the reason why I'm saying this is because I was a programmer for a decade. Then I went to do grad school in machine learning and data science. And I was like, oh, that's what this is. Why do they call it all these other fancy names? So I'm here to do a programmer's guide. I should have said a programmer's guide to machine.
And my favorite, before we get started, my favorite Seth Juarez quote is, AI is what you call it when you're selling it. Machine learning is what you call it when you're doing it. Did I get that right?
Yes.
There you go. All right. Yes. Feel free to steal that, chat. Great artists steal and all that.
Thank you.
All right. Well, let's get right into it, man.
All right. I'm sharing my screen. Can you pop it on? What do you think?
Yeah.
There it is. And I didn't prepare any slides.
Thank you for being so prepared.
We don't prepare for these kinds of things.
Yeah.
It just happens. It's organic. It's organic. So let's start with this. There are different terms. You've probably heard the term AI, right?
Yes.
You've probably heard the term machine learning, and you've probably heard the term deep learning. Yes. So the question is, how are these things even related? Well, let's pretend that these things are like a bubble. And I probably shouldn't say bubble during these economic times, but I mean, you know what I'm saying.
But it's too late. You already did, and now we're all super.
Dang it!
So thank you.
So AI is anything that gets computers to mimic humans. So that's the all-encompassing first thing. So machine learning lives comfortably inside of that. And then deep learning lives comfortably inside of machine learning. Okay, so let me change over to here to red. So for example, if you ever played a tic-tac-toe program, if you ever played against a computer tic-tac-toe, you could use standard AI to do that. Not like this old school AI is like a glorified search problem. I'll give you an example. Let's just say there's tic-tac-toe here, and I put my O here. A computer can say, here are all the other 1, 2, 3, 4, 5, 6, 7, 8 moves that the other person can do. And then based upon those moves, it can find out like what are the moves that I can do. And then it can search the tree and find the optimal path. This is called Minimax, and it's a glorified search algorithm. It's called adversarial search, and this is how most games are written, like easy games at least. Does this make sense to you? Like, stop me if I'm saying something.
No, yeah, it totally makes sense. I mean, right now, AI is an amoeba, ML is an amoeba inside that amoeba, and deep learning is the nucleus.
The nucleus, yes, as Nacho said in Nacho Libre. You got to reach a man's.
There is the soul inside of the soul is the nucleus.
Yeah. So it turns out that there's certain kinds of AI problems that are not searchable. Like, for example, tell me if this is a picture of a dog or Seth.
Looks like Seth. I'm going to be honest.
Yeah, it does. It does. But the thing is like this is very hard to figure out. And so machine learning is a class of problems where you don't program things. You give it examples of the right thing. It figures out an algorithm, and then that algorithm is used to produce outputs. So you know how when we write code, we're like, hey, let's write some code. And then this code gets, let's just say you're a Java person. This gets put into a jar file. Man, I am terrible at writing. Jar file. And then you take this jar file and you give it input, and out comes output. I mean, that's basically machine learning is a glorified lazy way of writing functions with data. Instead of you programming the thing, you give it examples and it figures out the algorithm for you, and that's it.
Okay. Yeah. So this is where it gets a little fuzzy for me because I know I'm a programmer, so I know that programs do what I tell them to do.
That's right.
And I put the logic in.
Yeah.
The program cannot do anything that I don't tell it to do.
That's right.
But in the case of doing image recognition, I literally don't have the skills to program and tell the computer.
That's right.
All of the logic, this pixel that's slightly this color, that's over here, like that would just be millions of code paths. And I am incapable of doing that.
Correct.
But you're saying the machine, is it actually generating the code when it does ML?
Kind of. And I'm going to show you exactly what it does here shortly using Visual Studio Code.
Ham horn. What's up, Alan? I love you too. Thank you, chat.
Alan, well, you throwing love to Burke and not me? Is this? Maybe it is the first time we've met, Alan. I'm just saying.
Alan doesn't just show up and say that they love you.
Yeah. Oh, it's got to be a relationship.
Earn it, and it's going to take more than Microsoft Whiteboard, which is where we are right now. All right. So you're going to explain how ML writes the code for us.
Yes. Yes. And then deep learning is machine learning, but with neural networks. So, for example, machine learning has these algorithms called neural networks. Deep learning is neural networks that are deeper. Now, the depth of the neural network for it to be deep learning instead of just regular machine learning really depends on the marketing team.
Okay. So deep learning, AI is what you call it when you're selling it. Machine learning is what you call it when you're doing it. And deep learning is what you call it when you're really selling it.
When you're really, like, it's like you're doing learning, but deep learning. Okay.
It's the hard sell.
It's the hard. So this is a helpful thing. I'm going to scroll up here and I'm going to tell you how it happens. So usually the way it works is we write some code, right? And we give it some input, and then out comes some output, right? So this goes in, this comes out. We usually write the code. Now, instead, so this would be like an algorithm, for example. Machine learning is different in that you give it the input, you give it the output, and out comes an algorithm. Then you take this algorithm, which is like a jar file or an assembly, you give it new input, and then out comes the output.
Okay, so you send in a picture and you say, this is Seth.
That's right.
And then the computer says, okay, here's the algorithm that I use to get that.
That's right.
And then you take that algorithm and you send more pictures in, and the computer says, Yes or
Yes.
no, this isn't Seth.
Yes. But you keep asking the key question, like, well, what the heck does this even look like?
Yeah, what is that? You say algorithm, but somebody asked me this the other day. They're like, "What is an algorithm?" Like a non-technical person, and I described it as being as like all it is the logic that a program uses to come
Correct.
to give you an answer.
Correct.
But what is that logic? We're developers. You can't just say it's an algorithm. What is it? There's code
Cool.
somewhere.
I'll give you one example. Like, for example, let's just say you're trying to decide uh, the if someone should, I don't know, if you want to accept them into your program or whatever. Like, let's just say there's the Burke School of Fine Dining, which I know you're going to be starting up soon, and I'm not trying to give things away. I'm so sorry.
And that's
So
okay.
so
Yeah.
the Burke School of Fine Dining, and you're like, okay, let's just see. I have Seth. Does he have enough hair? Right, and this is either yes or no. Right, and then you make another decision based on that. So this is, for example, this programming method is more like
Well,
a series
your
of
mic is
nested if
muted. I can't
statements.
decide if that's for the best.
You see what I'm saying? It's just like a series of if statements.
No, I don't think I think your mic is. I can't hear you. Jack,
Can you
can y'all
not
hear
hear me
Seth?
now? What? Can you hear me?
Olivia, can you hear Seth? I
One,
can't. I lost him. All right, hold on.
1, 2, 3, 4, 5. I can hear me.
What do we do? 1 second. Watch this. Watch this.
1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2. Now that Burke's away, I will continue. He'll come back. Oh, he's there. All right. Can you hear me now?
Yeah, I'm sorry. It's on my end.
I thought it was me. I was like,
I
can
didn't
you
know.
hear me? Hello?
Just a complete browser fail. Okay.
Hold
Sorry
on.
about that, Chad.
Maybe we should dial into the stronger
Look at
internet.
this. Look at this.
I'm
Seth
dialing into the stronger internet.
thing. Chad, do y'all know that? Do you
This is
recognize
more
that
power.
noise? Yeah.
Okay.
Man,
Now it should work.
I mean, so much nostalgia there. Really, I'm not even joking. Like I have actual feelings that come over me when I hear that. And they're very positive.
Burke, we're so old. It's not even funny.
I know. Listen, man. Get off the phone. I'm trying to use the internet.
Okay. So notice that this is like it's like a series of if statements, right? This algorithm that you're looking at, this is a structure like if else and then a nested if else. These are called decision trees. And what you can do is if you have a sense for your data, you can create generic decision trees that decide what columns of your data to split on and when to split on them. So notice that this is really easy to understand. You're like, oh, I understand this. So it's not that the computer is generating an algorithm. You have to pick an algorithm shape, give it the shape, and then it optimizes the parameters inside that shape to produce an answer.
Yeah, you completely lost me there. What do you mean by the shape?
Great question. So let's just say you have a sense for like this particular problem for people to join, Burke's Gourmet, because you obviously you're going to teach. You're a wonderful chef. You live in Tennessee. They have wonderful food there, and
Well,
you wanted to.
all we have is Nashville hot chicken. That's literally all we eat here.
And that's
in
all I
Nashville.
want. I mean,
Yeah.
Nashville hot chicken gourmet. If you want to accept people into your school and you were to write a program by that, and let's just say there's a row of features about the person coming in, right? What you would do is you could, in theory, write an if statement. If Seth has more than 20% hair and Seth, and basically you could create this nested if else statement. Like you could build an algorithm to do that, but you would have to look at each row. What I'm saying is, if you think that your algorithm is supposed to be that kind of structure, you can use math to automatically generate a decision tree if you have a label that tells it the right answer. So let me say it in a different way. So let's just say here's all the attributes of people coming into your gourmet thing, and then you have one other column that says yes or no or to accept them, right? The computer, what it can do is if you say I want to make it like a decision tree, it can take this block of data and automatically generate a decision tree based upon this information that you gave it. And so next time when
But
a new
how does it know, Seth? Like, how does it know what tree to generate? It doesn't know what all my qualifications are, because going down the tree, it may change, right? Is it like this? Yes. Well, then is it like this? No. Okay. Then is it like it's a complex flow chart? How does the computer not need to be told at every step, this is what you do?
Okay, so that's the next best. That's the next good question. So you're giving it all of the examples of the right thing. So what it does, if you want to know the actual math behind what it does, I'll tell you, because I think this is where people get a little confused, because like, how does it actually know? And let me do my red one here. Okay. Oh, oops, I didn't do the red one. So here's the red one, right? So these are the right answers. Yes, no, yes, no.
Wait, you put the right answers in red?
Oh,
That
yeah,
seems like a good idea.
it's a really
Do you want to
good
erase it?
point
Okay,
here.
there we go.
Really good point here. Let me just. By the way, I'm using a Wacom tablet. It's a pandemic purchase.
Isn't it a Wacom tablet? Is it a tuple?
No, it's a to play.
Okay.
To play. So yes, no, yes. Okay. So what it does is it looks at all of your data at once, and it looks at the messiness of your data. So right, you can measure a column how messy it is. That messiness is called entropy. And there's a way to measure that.
Wait, just real quick. What do you mean by messiness? What does that mean?
So for example, let's just say the first column is an ID column, right?
Okay.
That is the messiest column you have, because each number is unique and there's no
Oh,
information gained by understanding the ID. So you
it
would
doesn't
never
mean
put an if
anything at
statement.
all. You
Huh?
can't, it doesn't tell you anything about the
Nothing.
data other than it's a
It is the
number.
messiest data
Okay. Okay.
because there's no information to be gained. So
So
you
what's an
measure the
example of something
messiness.
that's not messy data?
Yes. So the way you measure what's the least messy, so you measure the messiness of the data, and then you measure the messiness. Let's just say this is feature X, right? And this is the right answer Y. Then you measure the messiness of the answer given this column. So does this column make this answer less messy? And I'll give you an example. So let's just say like there's yes hair and no hair. And so you have yes hair, yes hair, yes hair, no hair, no hair. And then you have the answer being like yes, we should accept them. Yes, we should accept them. Yes, we should accept them. No, we should not. Notice that if I were to give you this column exactly partitions the answer space really nicely. So I can decide
Oh,
based
it's
upon
almost an
hair.
exact replica. Yeah.
Yes. But the reality is sometimes it's more like this, no, like this. So you need to know another column, right? And so this is called the entropy of this data, is one thing. And then the entropy of this data, the answer, given this one. So what we do is that the computer looks at every column, and then it says, does this column make the messiness of the answer less? And it picks the one that does that the most, and then it splits,
Oh,
takes
and then
that
it picks
feature
the
out,
next one and
and
makes
it
it.
does the next one.
That's how it decides.
Yes. And so that's just an example of one machine learning algorithm called decision trees. But notice you have to have a sense for, this is the kind of data I have. So this is the kind of algorithm shape I want to give it, and it figures out the best representation.
Okay. So that makes sense. I agree. I like the phrase messiness. Like, that makes sense to me. I understand that, the messiness of the data, and I understand that the computer's looking for whichever one is less messy is the one that I'm picking. And then after that, whichever one is the less messy, that's the one I'm going with. And that's how it traverses the tree.
And there's different, what they're called impurity measures. There's something like entropy, there's something called Gini index. And information gain is how much information do we gain by putting this column next to the answer column together. So what is the entropy of the answer and the entropy of the answer given this column? And the one that maximizes that, we do a split and then we recurse.
Okay. I'm with you. I'm still with you, but just I'm hanging on by a thread, but I'm there, man. I feel like I'm there. So
Cool.
where do we go from here?
Cool. So so now that we know that thing, it turns out that doing this for a picture is not useful, right? Because pictures are basically 3D matrices where each pixel, right, has like another like RGB, right? And it turns out that for every pixel making a decision tree, the decision tree would be ginormous, and then it wouldn't be very good. So we've got to find a way to make a structure that takes an image, processes it, and then tells you, okay, it's one of four things. It's either a rock. I'm going to do rock, paper, or scissors.
Right.
And I have some data here to show you. So again, just to level set, it's not that the computer invents an algorithm for you. You have to give it a shape, and then given the data, which is the actual thing that's going to go into the function, and the right answer, it optimizes the parameters in that shape to give you the best model.
Okay, but the shape is still fuzzy to me. Like I still don't know exactly what that means. How do I give something a shape?
So in this case, you're saying, if you're using decision trees, you're saying, I want the shape to be a tree. Optimize for the best tree.
Ah, okay. So what are the different shapes that you can give it?
Great question. So there's different kinds of machine learning algorithms that are not neural networks. There's things like logistic regression. There's decision trees. There's some things called support vector machines. And all these algorithms do is they try to separate the feature space so that it can figure out how to get the right answer. That's it. And the decision tree, the feature space, let's just say the feature space, let's just say you only have two things, and let's just say here's all the ones that are accepted and here's all the ones that aren't, right? Basically, what a decision tree does is it separates the space like this. It separates it in half, right? Because that's what if it's on this side or on that, and then it separates it in half again, and then it separates in half again, right? Because that's what a decision tree does. There's other separators that separate things linearly, that say everything on this side is the answer. There's other things that take the feature space, project it into a different space, and then create like linear separators that kind of look like this, right? And then there's deep learning that makes a really weird separation over pixel space, which is so now I'm
going
not
back to the image example though.
Okay.
You said that you can choose the shape. So you said processing an image, we can't use a decision tree, right? No. That's what you said, because it's too complicated.
Too many if else. Like if your picture's too big, it's let's just say it's 24.
You could have, how many pixels are in a high res image, and then each pixel could be either red, green, or blue, right? And so that's too many. There's too many possibilities there.
Yes.
Okay. So what happens instead?
Oh, good. So in this case, neural networks are better at it. And what neural networks do is they take your image, right, which is basically a 3D matrix, right? Because this is red, green, and blue. And what they do is they multiply. It does a bunch of functions. So it does a function over this huge matrix, right? And then it nests it, and then it does like it takes this function, and then it does another function over it. And these are all literally linear functions, except for this one. And so basically it takes all of these pixels and it puts it into this multiplication space, and then it just builds networks on top of it that take every single pixel, multiply it by some magical weight number that we need to figure out, until in the end there's this vector that comes out where it says, okay, if the density here is highest, then guess this index, or this index. Now this is confusing, so I'm actually going to show you.
Okay.
And there's different kinds of neural networks. So I decided to fire up Visual Studio Code because that's what this show is about.
You're good on
context. The thing about Visual Studio Code is that you can literally
context clues.
You can literally just run the notebooks in here. And I wrote this thing last night super quick, right? So
in like 5 minutes, you wrote all that code in 5 minutes.
Literally this morning. So this is
Copilot, right? Make me a demo.
So this again, the way it separates it is you have to grab your data, you have to create your model shape, and then you have to give it the data and train it so it optimizes its parameters internally. Once it's done, you can save that model and push it out. So let's go through each line, and maybe I'll just go through the training here.
Can you bump up the font size for me?
Yeah, sure. Is this good?
Whoa.
No.
Maybe right there. That's good. Hide the sidebar.
Perfect.
Hide the mini map.
What I'm going to do is I'm just going to run through the code as if I was the computer.
Okay.
So I'm going to hit F5. And by the way, Visual Studio Code, I feel like I need to say something here. Visual Studio Code is a wonderful addition to a developer's toolbox. Not only did it allow me to get started with Python quickly and easily, but it understood the virtual environment. I can debug, I can go into things. It's literally a lifesaver for Python programmers.
Wow, we're gonna ship that as a new.
I'm gonna hit the bug for debugging.
We're gonna put that on YouTube.
Okay, so I'm debugging now, and I'm just gonna go into the main function F11, and basically the batch size says, because you can't give it all of the images at once in the universe, and so when this model is being updated, you're saying give it 32 images at a time.
Okay,
cool. F10. Now what I'm doing is I'm getting the data. I use training data to train the model. So basically, I push them into the model. It updates its internal parameterization.
What is that, like a CSV file, your data set?
No, it's a list of files of image. Oh, I guess I didn't show
image
you.
Files. These are images.
These are literally images. So here's the data. Let me reveal in File Explorer. So revealing. Hold on. View.
Pull it off on one of your 19 monitors.
I know. Okay. So these are the pictures. There's me doing nothing. This is my favorite one, by the way. This is Judgy Seth. Me doing nothing, right? Me doing paper. Me doing rock. Yeah. Power to the people. And then me doing scissors. Oops, that's rock still. Scissors. So that's the data.
Okay.
And what get data sets does, I think we'll just F11 because I mean we're here, right? F11. It gets the data images, right? It pulls the right thing out, and then what it does is this transformation takes the image file and it converts it into what's called a tensor or that 3D matrix.
Yeah. And so tensors, for y'all chat, I'm going to explain tensors here for a second because I just researched this, but tensors, as best I can, and tell me if I have this right, Seth. A tensor is a type of data structure that's, you can think about it like an array, but it's optimized to run on special hardware really fast. Yes. Would that be an accurate description of a tensor?
Yeah. A tensor is just a glorified array with subarrays.
That was huge for me because I was always like, what the heck, TensorFlow? What is that? I don't know what a tensor is. That sounds super complex. And somebody was like, no, it's just an array that's optimized to run really fast on hardware.
Correct. Well, on GPUs.
On GPUs.
Because remember, it's basically a 3D tensor. That's an image. It's like here, I drew it before, and I want to emphasize this. This is what an image is. Think about it. They compress a little bit, some of this, but if you uncompress it, you basically have 3 matrices, one for red, one for green, one for blue.
And so the tensor is holding that.
It's a 3D tensor.
Gotcha. Okay. Yeah. All right.
And then we make it a 4D tensor by adding a batch. So the 4th dimension is, this is picture number 1. Here's a 3D tensor.
Oh, okay. Yes. So the first 3 dimensions contain one RGB image, and then the 4th dimension contains a bunch of different images.
Yes, yeah. So it's like an index to all the images. And so basically a batch of images is basically this thing, but then there's like another tensor inside of it that has, like, for each image you have this thing. And that's why it's a 4D tensor. And for example, if you think of a video, right? That's a 4D tensor because you have RGB over time. And if you have multiple videos, that's a 5D tensor.
Okay, that makes sense. But when people use words like 4D tensor and linear regression, the rest of us out here like, nope, hard pass, no thank you, because we don't know what any of that means. At least that's how I feel, right? When it's like introduction to TensorFlow and all this terminology gets thrown around, I get really turned off. I don't know why I'm telling you that.
It's
not
okay.
like
we're having a moment where we're
yeah, heart to
discussing.
heart. I just want to tell you why I don't feel very, very smart most days.
Hold on. Tell me again.
Well, it just feels like everybody's using very large words that they made up just to make the thing sound more complicated than it is. And I understand why we can't just call it a very complicated array or a special array that runs very quickly.
It's the 10K salary bump.
Right. Why does it need to be a 4D tensor?
Because we need to justify our salaries.
Right. No, it's a very hard job. I work with 4D tensors. Yeah.
We work with 4D tensors. Show me the money. I don't know.
Put that on your resume.
You're right. Yeah. These things are done. I don't understand why we make these things harder than what they do.
Okay. Like even because I know as a developer, I know lay people don't. This is why lay people don't like to have conversations with people in tech. Yeah, large words make people feel better. Exactly.
Yes.
And so, but this is why people don't like to have conversations with programmers because we tend to talk this way. But even as a programmer, I don't like to talk about data science because people that talk about data science talk to me this way. I'm like, I don't know what you're talking about. I don't know what you're talking about.
Well, I mean, now that I said 4D tensor, you're like, oh, a video file?
Right, exactly. You could have just said a video file. Right?
Yeah, but the reason why we have to say it in this way is because the structure that we've chosen to be able to do the predictions requires it to be in the shape.
And I understand that. Yeah. That does make sense. Yeah. Yes.
Yeah.
Okay.
So this thing, what this does is this resizes it to 256 and then it crops it so that every image is going to be 224 by 224.
Okay. So you're resizing it and cropping the edges off?
Yes.
Okay.
And the reason why is because this isn't magic. It's still a function. You can't give it an arbitrary picture. It needs to be an exact size and an exact shape.
Okay. And so is it because you're just trying to reduce the amount of picture that the thing has to process?
Yeah, I mean, I could change this number. This parameter I could change to be something bigger or smaller. These parameters you can adjust and tweak to see if your machine learning algorithm does better. These parameters are called hyperparameters. Hyperparameters.
That's even worse.
I know. That's why I did the sound, man. Hyperparameter. These hyperparameters are things that you can tweak the knobs of so that when it does it finds out its best shape or the best tree or whatever, it does better or worse. Now you're starting to get the sense where this feels like a lot of guess and check. Yes, that's why it's called data science, because science is glorified guess and check. And a data scientist most of the time is tweaking these stupid things and making sure the data is in the right shape. This here.
So that's what it's doing is it's guessing. It's saying, I think this is the answer, and then it's testing. Is it the right answer?
The data scientist is doing that. They're saying, I'm going to guess that 224 is the best shape. And that's people have figured that out. And look, I've been with people that have won Turing Awards with this stuff. And I've asked them pointed questions, and they're like, well, you kind of just go with what people have used before. I'm like, that's not very scientific from the guy that won the scientific award of the century. It's like the Nobel Prize for our field. And you're telling me just guess.
Yeah. Well, I mean, it is 2022. So
maybe it's changed since then.
Right.
But anyways, and then what this does is this, instead of having the pixels be from 0 to 255, this normalizes them so they're like between 0 and 1. Because if you have really big numbers, it kind of skews stuff. And this is just something that we found empirically. So that's what this does. This is transforming this is transforming the input. This is transforming the output. And then this just loads the raw data. And the raw data, you can see it has the classes, rock, paper, scissors. It has some of the images in there. And then these are the raw data classes, which are none, paper, rock, scissors. You're like, how does it know that? I'll give you a hint. Oh, that arrow is pointed in the wrong way.
Hold on, I've got someone. So I have this like internet connected light bulb, and someone got the API key, and I know that because it's going crazy over here. So I have to go in and revoke the key. But you do your thing.
The key to what happened?
Well, I have an internet connected bulb over here, right? And I made this website for it called I Love Lamp. You've seen this.
Yes,
right?
I have.
I'll just type it in so people can go there. But somebody got the API key, and I know that because the lamp's over here and it's just like flashing and going crazy. And the website does not let you do that. The only way you can do that is if you got the key. So I'm trying to revoke the key, Seth, before I get charged $1 million.
Just be like, yeah, every once in a while.
All right, go ahead. Sorry, we're
okay. So this gets the size of the data, training, validation, and so this basically does a random split. This is the validation data set. This is the training data set. And I return all these things, and then you get a training, and these data loaders just load the data out. So this is just a fancy way of getting the data. Now, this is where it starts to get a little interesting, right? Because this is where you get the beef of actually doing this stuff. So I actually have a GPU. So you can see that my device is going to be CUDA. And then this function here just says, how bad are we at doing it? And we want to minimize our loss with respect to the parameterizations of the model. And you're probably thinking, well, what the heck model are you doing? I'll show you. This is the model. We're using a standard base model that someone has already used. And we're adding a connected layer over at the top, at the end. That basically what it does is it will output. So in goes the picture. In goes the picture. It goes into this neural network thing. Out comes this vector of size 4 that says, okay, if it's none, this is the biggest number. If it's rock, this is the biggest number. Scissors, etc. So I'll keep going because this is just take for granted that this is the model shape that I've chosen, and I know it works.
Okay.
So we'll init that. Boom.
And so when you're choosing a model shape, is it basically like you have to have some knowledge of what your options are, and you have to know kind of like what they're best for. And I assume a Google search will get you that. And then you just try the one that you think would work the best.
Yeah, let me show you something. There is something called a model zoo that shows you all kinds of different shapes and what they're good at.
But how would you know? What are you going to click on every one of these and try to read and understand the shape? How do you know?
No, I mean, it's kind of like after you're programming for a while, you know, like, I don't need to write a class for this. I could just write a function. Or, you know, like, oh, I need to use some pattern, right? You get, after a while, you kind of get a sense for, like, I look at this.
You see it, like, and
I look at this, and this is a GAN. It's a generative adversarial network, which means that this thing produces things for you. Like, it makes images for you. This RCNN, I know, is for object detection. So looking for things inside of objects and giving you their bounding boxes. I know this. Reinforcement learning. Okay, this is something where instead of giving it all the data at once, you give it data as it goes, and it updates its model as it goes. You see, and so you just you look at this, you're like, YOLO, what the freak? This is another object detection algorithm. You just kind of get a sense for what they are.
How, Seth, where do I go to learn all this stuff?
You kind of just, it's the same as a programmer, right? Like when you start programming, you're like, I now know what a function is. Oh, I now know what a class is. But after a while of doing things, you get this hoarse sense of compositionality. You get this hoarse sense of execution order. You get this hoarse sense of location of where you should put things. for example, and you just sort of I don't know. It's like saying, how do you become like a really good chef other than attending your class?
Yeah, you just cook, and you just know how much to put in and how much to not put in, and what things
Yes.
go together. And I gotcha.
Yeah.
Makes it you do it. You have to do it.
Yeah, and like I'm telling you, like I'm looking at these things, and you're like, oh, these two look the same. Yeah, because they're RCNNs and they're for object detection, segmentation kind of thing. And so
Okay.
that's how you kind of get. And then there's like categories, like for example, the hottest stuff is an NLP. They're called large language models, right? And they use some cool stuff.
So would that be like GPT
2
3,
and 3, yeah.
2 and 3?
Mhm.
So like Copilot would be natural language
Large
stuff?
language model.
Yeah. Okay.
Yeah, but a large language model over code. And so you kind of get a sense for what these things are after doing them. Okay, so there is the vision model. Looks like I wrote some code twice that I didn't need to. Here's the model. You can actually take a look at it. It's all in here. Here are the classes, right? Here's the fully connected layer. Here's the transfer layer. It's all in there. And then what you do is you continually optimize the parameters inside it. So you train it with the batch. You train it. You train it with a bunch of images. So I'll go in there and show you what it does for training. F11. It loads the data. And for each picture in the batch, this is the picture. This is the right answer. It looks at the model. It finds the prediction. Oh, it's going to take a second. It finds a prediction, and then it says, how bad are you at it? So this is what we predicted, and this is the right answer. How bad are you at it? Okay, now what we're going to do is we're going to optimize those parameters with respect to the loss function. And then it does that, and it keeps doing that, and it just gets better. So it says, let me run the model. How sucky are we at it? And then it tests it. Okay, we're still sucky. Let's optimize the parameters.
Okay,
And
but where is all that saved? Where is the model?
Oh, great question. So after we do the training and the test, I say model.save, and basically I say torch.save, save your internal state representation to this file, and there's the file right there. I also save the class. It's right here.
What happens if you open it? What does it look like?
I'll show you. Reveal in File Explorer. There's a really nice program written by Lutz Roeder.
Tell me it's YAML.
No, this is a path file. These are this is Lutz Roeder wrote this, and I can look inside of each of the modules, and each of the modules has basically numbers that it multiplies pixels by, and it puts them into a shape. Like these are just
the raw file look like though? Is it some proprietary? What is it like?
Well, I mean, you can see that I open it. I mean,
that's not what what is it? What does the text look like? Though? I'm interested. Like, is it XML? Is it JSON? Like, what is it?
It's just bits. It's like Python bits.
Is it?
It's like it's
binary.
Yeah, it's binary, and it contains invisible Unicode characters.
Yeah, it does. Several.
Yeah. So basically, there's the shape, and then there's the actual numbers that are packed in there that it learned to multiply these pixels by.
And why is it in that format? Is that just to optimize?
It's just a format. There's other formats there. If you want to look at the PDF of deep learning, the Onyx file format is probably the best one for interoperability. TensorFlow spits out PB files. It depends. It's like saying I have a spreadsheet. Okay, what's the file format? Well, it depends how you saved it.
Starts with PK. Think of this zip file. Is it a zip file?
Huh?
It starts with PK, so it's probably a zip file. Is it a zip file?
This one? No, it's just a binary representation of the neural network.
Don't lie to us. If it's a zip file, you just tell us the truth.
It's not a zip file.
I'm saying it's a zip file.
It's not a zip file. And then the other thing I saved, just to be helpful, is I saved the class representation. So index 0 is none, index 1 is paper, index 2. But if you notice, it was kind of pretty crappy at it. Like it got pretty bad accuracy. And the reason why is because we only trained it for 5 epochs. So now I'm going to train it for 20. I'm going to let it like continue to learn.
So just by making it do the same thing over and over and over again?
Yep.
Like practicing the piano.
Exactly.
Or in Seth's case, the harmonica.
Okay, is this doing the thing? Here we go. Okay, so now it's going to start again. It's using a CUDA device, the GPU, and you're probably thinking, why does it need a GPU? If you ever played video games, all that's happening in there, if it's a nice video game, is it's basically multiplying a lot of matrices a ton of times.
Yep.
And GPUs are super good at that. And so that's why GPUs are super good at machine learning.
So they've just been kind of repurposed. They just sort of figured out, oh, this hardware type, which is really good at pushing textures, which are really complex.
Yep.
Is also really good at, okay.
And notice that it got better. The more time we gave it to learn. I bet I could have it go to like 30. And let me do 30.
It's at 97% already.
I know, but this is such a stupid problem.
All right, so look. So we can land this plane, and also because true story, I have to go pick up a margarita machine for a party this weekend. That's not. Okay. I wouldn't make that up.
One more thing, because I want to show you loading the model and using it.
Okay.
So maybe I shouldn't have started this, but basically here is as it's training. I'm loading the model from the path. I'm loading the classes. I'm doing the same transforms that I had before. An image is going to come in. I'm going to change the image to a bunch of bits, do the transform, run the prediction with this model, get the argmax out of it, and that is the index to the actual class. So let me run this so you can see it. F5 here, just to finish, Python file. By the way, isn't that handy? So I initialize the model. I load up the model. I reinstantiate the model class. I load the state dictionary from the model file. And then I do the same compose because that's how we trained it. And now we're going to try to find this image, which is me doing scissors.
And see what it tells you that it is.
Load the image. I pull the image from the web. I open the bits. I do the transform. I call the model. And this, you're looking at this, you're like, well, this is unsqueezed. What the crap? Well, it's expecting a 4D tensor because it was trained with batches of images. So I basically add a fake. I say, okay, I add a fake dimension that says it's one picture.
Oh, because it's only one picture. It's not a bunch of
pictures. I get the response, and look at the response is a tensor. And the tensor is like an array that says, which is the one with the highest index? That's the one we guess. So I get the argmax, which gives you the index, and it says that indeed is some scissors.
So go back to the response and look at the tensor. So because it looks like the highest score in the tensor is 9 points. It's the fourth one.
Yep.
It's scissors.
Yes.
So that's none, rock, paper, scissors.
Yes.
So man, it almost thought that was paper. Like it was really close.
I should have, I don't know why I didn't print it. I should have printed it. So let me just run it here. So you can see that it does, here it is. It thinks it's scissors. Let's do rock. Not rock, it's just rock. See?
Oh yeah, the score is a lot higher on paper.
Yeah, you see, this is the highest score.
Yeah.
And so that's the one it picks because that's what's coming out of the neural network. And this is called deep learning for classification.
Okay. One question that I want to ask about all this stuff, Seth, is that I understand, or at least it's been told to me, that one of the problems with AI or with neural networks is that we are not exactly sure how the computer came to the conclusion that it came to, how it got.
Well, we are sure.
We know for sure.
We do know. We do know exactly how it does it. The problem is that it's tough to analyze. And this thing only produces the best model with respect to the pictures you gave it. And so if you were to give this a picture of you, it would suck because it only knows my face. So just to get into responsible, ethical AI with classification and computer images, if you do not have a diverse set of people playing rock, paper, scissors, the model will fail. And if this particular style of model can create harms, that's when you get into some of the irresponsibility. And no, we know exactly mathematically what it's doing. The
So
problem is that it's hard to analyze because it's assuming that you're giving it all the data that it needs.
wait, Seth. It's not going to be good at rock, paper, scissors if you give it pictures of me doing rock, paper, scissors?
No, because it optimized for the pictures that I gave it, which are pictures of me.
But I'm doing okay, so this is what's interesting to me, right? Human beings would be very good at this. It wouldn't matter what you looked like. Rock, paper, scissors is rock, paper, scissors. And once you show somebody what that is, they would be able to identify it no matter who's doing it. But you're telling me that the computer, and if we both do this, right? If we do this, or we do this, or
Yes.
this is going to look really similar. I mean, really similar. But the
What if you're a
computer
person of
can't handle
color
that?
and the background is dark? You see the
Okay,
problem?
so it's because of the limitations of.
No, it's because the I have told it mathematically optimize for this set of pictures, and it has no feelings. It doesn't care. It just if I were to give it a picture of a dog and say that's scissors, it would say that's scissors every time. But then if I were to give it a picture of a cat, it wouldn't know what to do with it. It would say, "Oh, dog." It
Right,
has no
which makes
feelings.
sense,
It has
right?
no
It's like
emotions. It doesn't think. It's dumb. It's just the problem with the way we market this stuff today is we imbue it with human attributes
which it
that it
doesn't.
neither
Yeah,
has
it is
nor
not
could
that.
ever have.
Yeah, it is not that. And I do this too, right? Like I think it's an AI. Like you can't figure this out. It's like, no, it can't figure it out because you haven't told it what it is. It doesn't recognize that, and it cannot figure that out from something that it's seen. You know what I'm saying? Like human beings have this ability to extrapolate and to figure things out based on a lot of different inputs at the same time so that we could recognize rock, paper, scissors anywhere on any one. But you're saying a computer cannot do that. You
No.
actually have to give it
Yes.
all of that.
Yes.
Huh.
It has no feeling. That's why when people say, "Oh, it just does it," when you anthropomorphize AI, you are shifting responsibility away from humans. When the reality is, I gave it the pictures that I gave it. It only recognizes a weird bearded Mexican guy. That's it. And that's the super important part to take away from all of this is that we have to be responsible with how we use this and why we use this. Because that's why when people say, "Oh, we don't know what it's doing," that's a really cheesy way of shifting the responsibility for ethical AI over to the machine. So I don't do that. I know exactly what it's doing.
So
It's taking a bunch of images, multiplying it by numbers, running a bunch of functions over it until it reaches the output state, and I've optimized it using linear algebra and calculus.
yeah, I'm looking at chat. Chat's asking, do you have an example of this project? Somebody else is like, Seth knows how to make a Rochambeau API AI.
Yeah, I did. In fact, let me open up. I actually for those that have watched the AI show, we've been building this for a long time. So I think it's github.com. Let's see. I think it's AI Advocate. There it is. This is the actual website. It's full. It's a full thing. I'm gonna start the AI show is gonna start up again. We stopped the AI show for a little bit because there was these things going on in the world, and I didn't think it was appropriate at the time. And so, but yeah, this is all the code in here. But this code is a little bit more intelligent than what I showed you because I kind of wanted to slim it down a little bit. But here, you can see the model code right here.
Okay, there it is. So people can pull that down and mess
Using a
with it
different
themselves.
model, VGG19.
Oh yeah, the VGG19 one. Yeah, Seth, man, thank you so much for coming on. I wonder, Chad, if should have Seth come back and talk about ethical AI. This is something that's interesting to me, and like I don't even know how far down this road we can go, but I stay concerned about AI, and here's why. It doesn't have values or morality, and nor can you program those things in, right? And so
You
it
can
can't
try.
look at something and go, okay, that's the answer, but I know that that's wrong because that's a generalization, And I should not apply that, right? It's literally going to apply a generalization to people based on attributes that you don't really have any control over. And that seems worrisome to me.
And the worst is, I'm not using gender or race, but if you're using zip code, you might be.
You still, right? And we already do this, right? So say like car insurance. If
Yep.
you're a young male, your car insurance is significantly higher, at least in the state of Tennessee. And I know that because I have 3 boys.
Yep.
Why? Because young males have a propensity to get in accidents. Like the numbers just don't lie. Like something like 90% have an accident in their first month of having a driver's license. This is really high.
It's just math.
But my kids are now paying well, by my kids I mean me. But
yeah.
Anyway, seems like there's a lot of tenuous area here.
And so that's the question. And so that's why when we got to the end of it, I was pretty dogmatic. Yes, I know exactly what it's doing mathematically. I can actually look at the individual numbers and we can do the analysis. When people say, I don't even know what it's doing, what they're saying, but they're not really thinking about is what you're saying is you're disclaiming responsibility for what it's actually doing. You can't do that.
Yeah.
Because what if this algorithm were to predict something important, like whether you should get healthcare or whether you get housing or whether you should, you see what I'm saying? All of a sudden it's
already doing that. Aren't we already doing that with
I'll give you one example. If you're using machine learning for recidivism, terrible idea. Terrible idea. Recidivism is someone repeat offending and coming back to jail.
Right. And that's the one that sort of bubbles to the front of everybody's mind because we already do that. And I didn't know this, but I had a friend that worked for a consulting agency for the state of Tennessee, and they worked on the system. When you go in and you have an offense, it looks at all that stuff and it makes a recommendation to the judge on what your sentence should be based on a lot of factors. I'm like, wait a minute, the judge doesn't do that? The judge does do it, but the computer recommends. I'm like, that's freaking terrifying.
Or what if you build an AI model to tell you where you should go police?
All right, chat.
Problem? I'm just saying, you give it the data.
All I see is problems.
I know.
Okay, chat. Thank you so much for being with us. Thank you, Seth. We appreciate it. We know you're busy prepping for Build. Y'all, can we talk about Build? Can they go register for Build?
Yeah, you can register today. In fact, I'm helping out with a keynote and some sessions on AI, and we are going to be doing something really fun.
Well, you'll have to join to find out. I'm going to guess it's going to be rock, paper, scissors, but what do I know?
It's better than that. Day 2.
All right. Hey, y'all, thank you so much for being with us, chat. We'll see you back here next week, and have a great one. Bye.